So we talked about the Diels-Alder reaction, and that's a 4+2 cycle addition. There's one more cycle addition we're going to talk about. Now there are more, but these are the two most common, the 4+2 and the 2+2. So again, all of these reactions, the mechanism is very straightforward. With the 2+2 cycle addition, we are again taking 2 pi bonds and converting it to 2 sigma bonds. So in this case, we're only starting with 2 pi bonds, and we form cyclobutane. Now, cyclobutane does have our ring string, whereas our Diels-Alder didn't. Diels-Alder formed a 6-membered ring. The mechanism, again, these are always concerted, so our mechanism just looks like this. Here we only see 2 pi electrons participating in the reaction. And then we form, these are our new bonds shown. And we can have groups attached to these positions. Now this reaction to occur has to be symmetry allowed. And we looked at that a little bit with the Diels-Alder. So our HOMO and our LUMO of our 2 starting materials have to come together to form those sigma bonds. So the like symmetry has to happen. So remember with the Diels-Alder, what we looked at was our HOMO of our diene and our LUMO of our dienophile interacted. And when we formed our sigma bonds, we were able, under these conditions, for us to have symmetry allowed. So that's what symmetry allowed means. But if we look at this reaction, we're starting with 2 ethylenes. We don't have a diene and a dienophile, we have 2 ethylenes. So the HOMO of one ethylene has to interact with the LUMO of the other ethylene. Now again, there's multiple ethylenes in this sample, since this is just 2 of the same molecule reacting. Now if you look at this, if it's symmetry allowed, this actually doesn't happen, because there's no way for this LUMO and this HOMO to interact, because if this red and this red overlap, then this is a red and a blue. So that doesn't happen. So why am I showing you this reaction if it can't occur? Well, because under these conditions it can occur, but under like conditions we actually can't get a reaction occur. And we used to do this one in the lab, but it never really worked that well as far as the conditions we were using, because we never have enough sunny days for it to do. But if we use enough UV light, we can make it occur. So this reaction actually doesn't occur under traditional reaction, which would just be as our traditional organic conditions. But it can actually occur under light. So what happens to a molecule when you use light conditions? Well, when you use light conditions, one of the electrons in our HOMO is going to be promoted to our LUMO. A couple of things with this. This means that an unpaired electron is in a higher energy level than it should be. So this never lasts for a long period of time. This is a fleeting thing, but it can react when it's in this position. Eventually, if this electron doesn't react, it will just fall back down. We call that relaxing back to its traditional state, its ground state. So this is what we call the excited state. The electron has been excited to a higher energy level, and now this would be considered our HOMO. And for this structure, we don't have a LUMO because we don't have a higher energy level. So now our HOMO is this higher structure. So before this relaxes down, it can interact with another molecule that's not excited, and therefore our HOMO and our LUMO can overlap because they're the same orbital. So the orbitals can overlap and be symmetry allowed. So the 2+2 cycle addition only occurs under light conditions because of this symmetry. Now again, remember, at any given point, only some molecules under light conditions are going to be in this excited state. So there'll still be plenty of ethylene that's not excited to react with this one, because this doesn't last very long. So this is symmetry allowed. So we can use our orbitals to understand what's happening. So those are our 2 main cycle addition reactions that we've discussed. Our next reaction is going to be our electrocyclic reactions. You can have electrocyclic reactions that have more pi bonds than this, but here's the 2 that we're going to mostly focus on. In the cycle addition reaction, where we're starting with our 3 pi bonds, we form a 6-membered ring. And the one where we're starting with our 2 pi bonds, we form a 4-membered ring. Notice we're forming a new sigma bond between our N carbons, forming a ring. And notice that overall, we're losing 1 pi bond and forming 1 sigma. Now here we started with 3 pi bonds, so we are left with 2. Here we're only starting with 2, so we're only left with 1, but we lose only 1 pi bond. If we started with 4 pi bonds, we'd still only lose 1 and end up with 3 pi bonds in the end. So overall, we are losing 1 pi bond, forming a sigma bond. Now again, with these things, our orbitals and symmetry is going to be very important. In the top one, our equilibrium favors the product, but in this bottom example, our equilibrium actually favors the starting material. So if we're looking at these, one thing we're thinking about is thermal dynamics. So which of our products are more stable? And for both, we're losing a pi bond and forming a sigma bond, which is typically lower in energy. But if we look here, from here to here, we have a 6-membered ring, we don't have a lot of ring strain. But if we look at this example, even though we're losing a pi bond, we form a 4-membered ring that has a lot of ring strain. So while this one is favored equilibrium forward, just because we don't have an issue of ring strain disfavoring it, this one isn't as stable because of ring strain. Especially because it's a 4-membered ring with a double bond in it. And remember, this angle is usually trigonoplanar, and you can see that this is a 90-degree angle, and it's really unstable. So that's why the second one isn't as favored at equilibrium. Now, we're going to look at the orbitals, and again, we need symmetry. But in this case, it's always going to work. The difference is going to be our products. So, determining our stereochemistry, if we form stereochemistry, is going, and of course, we're forming a ring, so we need to consider if we have any groups attached, if they're going to be on the same or opposite sides of the ring. And depending on whether we use heat or light conditions, will determine which stereochemistry we form. So we're going to look at this by looking at our molecular orbital diagrams. And when we look at the diagram, it actually makes a lot of sense as to what we're going to form. So this isn't something you need to memorize, we're going to look at it. But if we start with this one compound, under heat conditions, we form cis. Under light conditions, we actually can form trans. So what's causing a difference in our stereochemistry products? So let's first look at heat conditions, because again, that's going to be without promoting an electron to the highest energy level. So here are the molecular orbital diagrams for our, and it doesn't matter, again, this diagram is going to look the same, no matter what these R groups are, because we're only drawing these 6p orbitals. This can be 16-member carbon chain, but we're only looking at these 6 pi orbitals. So this could just be an R group, and it will not affect our molecular orbital diagram, because we're only looking at the pi electrons. And there's no pi electrons in these carbons, so we're not looking at them at all. So this is our molecular orbital diagram for a 6p orbital system, and this is always a molecular orbital diagram for a 6p orbital system. We have 3 conjugated double bonds. This is what it's going to look like, no matter what else is attached. So we filled in our 6 pi electrons, bless you, and we labeled our HOMO and LUMO. Now in this case, we're not having 2 reactions interact with each other. We're just having a rearrangement of where the electrons are in a molecule to form that ring. So we're only looking at the HOMO, because it's not reacting with anything else, it's reacting with itself. So when we look at the HOMO, when we draw it in this structure, we're going to retain the pi bonds that are here. If we look at this reaction again, notice that these p orbitals are retained in the product. So they're not changing, but the difference is that these 2 unhybridized p orbitals have to form a hybridized orbital to form this sigma bond. So overall, with our orbital diagram, the only change that we're seeing is this new sigma bond forming because these pi bonds are retained. And there's no difference in that product with them. So to visualize that, what has to happen is, remember, our sigma bond, our p orbitals are side-by-side overlap, but our sigma bond is head-on overlap. So basically what has to happen orbital-wise is these p orbitals have to either come together this way or come together this way to form a new sigma bond. And the way that they come together, and we have terminologies for that, is determining on what these orbitals look like and symmetry allowed. So a red and a blue can't come together, that's not allowed. Only a blue and a blue or a red and a red can come together. Or if you're drawing it in your paper, a shaded and a shaded, or an unshaded and a non-shaded, because you don't have to use the red and the blue. So that would be symmetry allowed. So the N carbons have to come together to form a sigma bond, and that's represented like this. When our two orbitals have to come together in opposite directions, so for the red and the red to come together, the way this one's shown is shown like this. This one has to turn clockwise, whereas this one has to turn counterclockwise. So we call that disrotatory, when they have to turn opposite directions, if you were to map that out as counterclockwise and clockwise. And that's the only way for the orange and the orange to come together. Now, how does that affect the R groups? Well, in this case, when they come together like that, that puts the CH3 groups on the same side. And that's why it ends up being cis under these conditions. Now, you will get both enantiomers because it's also symmetry allowed to have the two blue groups come this way. Here we're showing the two red, but the two blue are also allowed. But that's still going to lead to the cis product just with the two CH3 groups pointing up. In this particular case, we have a meso compound, but if these two groups were, let's say, an ethyl and a methyl, then we'd get both enantiomers, but only the cis product because of the way that it's turning. If we start with, or if we try to show conrotatory, which is turning them both clockwise or both counterclockwise, what we get is symmetry not allowed. So under heat conditions, for this particular compound, if we look at the molecular orbital diagram, only conrotatory is allowed. I mean, disrotatory is allowed. Conrotatory, where they both rotate the same way, will give us symmetry disallowed. So either both rotating clockwise, or if they both rotated counterclockwise. So for this example, we'll never get trans because this is not allowed based on symmetry. We have to have like overlap. So depending on what we start with, that's going to give us a different product. Now that was with our 3 pi electron system. With our 2 pi system, then we have a different molecular orbital diagram. So this is what that 2 pi system looks like. And this is our HOMO, so this is what we're going to look at. So depending on what we start now, notice with this system, for these two to come together, they actually do have to turn conrotatory, because the HOMO is different. So let's look at that example. So this is just redrawing exactly what I showed here for the HOMO. So if we look at this one, for the blue and the blue to come together, then they have to turn the same way. And then that ends up with, in this case, trans. If this one's turning clockwise, that puts my CH3 group pointing below the ring. And this one's turning clockwise, that puts my CH3 group up. So that's why for this one we get trans. Whereas for this one, again, we're still turning conrotatory, but the difference is where the CH3 groups were originally connected. Remember, we do not have free rotation around this bond. So when we actually have the reaction occur, here we're going to get cis because this one started pointing down. So when we turn it clockwise, it's going to be up. This one started also pointing down, so when we turn it clockwise, it's also going to be up. So it's based on where our groups originally started. So under heat conditions, this 2-pi system based on the molecular orbital diagram has to be conrotatory. You don't need to memorize this because you could just draw the diagram and see what symmetry allowed. If we look at this system, again, this is going to look exactly the same way no matter what the R groups are, because we are still only mapping out these 3 conjugated pi bonds. These are our only unhybridized p orbitals, so that's all we're mapping out. The rest of the R groups we're not looking at. So all I did was take that and put my orbital diagram in it for my HOMO. Notice my 2 nodes, exactly like this is showing. And for this to come together, it has to spin disrotatory. One has to go counterclockwise, the other one would have to go clockwise. Since these 2 CH3 groups are where they are pointing, what we'll end up with is cis. And the way I'm showing it, the 2 blue are coming together, so it's pointed up. But if I show the 2 non-shaded coming together, they'd both be pointing down. So either way, it's going to be cis. You're just going to get both enantiomers. So you would draw both enantiomers for that product. Again, notice these 4 pi bonds are staying the same. So we still have those conjugated pi electrons. Now, under light conditions, we're going to do the same concept, but now remember, under light conditions, our HOMO is the excited state. Now, under light conditions, you're only ever jumping from the highest occupied orbital to the lowest unoccupied. Under light conditions, you're not going to jump even higher. So now our HOMO is the higher level, which means that if you look at the higher level, the end p orbitals are going to be opposite from the lower level. So notice we don't care about what's in the middle, we only care about the end. Here, the 2 red are pointing up. Here, the red's up. Here, the red's down. So that's why under heat and light conditions, we get opposite products. Because the orbitals look opposite because of symmetry. We have 3 nodes in this HOMO. So now, only the conrotatory is going to be allowed. So if these 2 CH3 groups are pointed the way they are, when this one turns, that CH3 group is going to be down. When this one turns the same direction, both in this case counterclockwise, then the CH3 group is going to be pointed up. And again, we're going to get both enantiomers if it is not a meso compound. In this case, it is. And this one's not showing the pi bonds. It should be in there. Why they're not there. Oh. So if we look at this example under light conditions, again, our HOMO is now this example. So all we have to do is look at these 2 ends. All I did was redraw everything, but really all you need is the 2 ends. So I'm showing my red as unshaded, it's up, and then my red is down. So again, this would be our conrotatory, and that'll lead to the trans. When this one turns, the CH3 group's pointed down. When this one turns the same way, that makes that CH3 group point up. Because it's connected. The CH3 group has to do whatever the carbon does. And again, you're going to get both enantiomers. You can use the same, now this looks very similar to the example here, but the difference is the amount of p orbitals. So here we have our 3 conjugated double bonds. Here we only have 2. So we're only mapping out these 4 p orbitals. So that's going to form our 4-membered ring here. And under light conditions, our 4-membered ring, our LUMO is this higher one. So in this case, our disrotatory will be allowed. When we turn it for our orange to overlap, that makes the CH3 group. If we turn it this way, that'll point my CH3 group down. If this one turns this way, that'll put it down. So we're going to again form cis. And again, you're going to form both enantiomers. And our group that's connected in this case is an ethyl group. You can use this table But if I ask you a question like this, I will ask you to map out the molecular orbital diagram and explain to me why the answer is what the answer is. So this just summarizes what we went through, but it's really not necessary to memorize it because if you look at the molecular orbital diagram, you can figure it out. The last one we're going to look at is the rearrangement product. Now again, this is a rearrangement. It's our only product in these electrocyclic reactions that will not necessarily lead to a cyclic product being formed. So our rearrangement is a rearrangement. And the difference is where the pi bonds are, but overall we have the same amount of pi bonds and the same amount of sigma bonds that we started with before and after the reaction. The difference is where the pi bonds are actually located. And this is the only example that we are not starting with a conjugated pi system in the traditional sense, but it's still going through the same mechanism. Again, this is our mechanism for all of our electrocyclic reactions. It is a closed loop, no intermediates. All you do is put the arrows into the starting material. So in this case, for this first example we're looking at, what we see is we're breaking this sigma bond, and we're forming this sigma bond, but our pi bonds get rearranged. So our transition state does look like those other electrocyclic reactions, even though we're not starting with the traditional conjugated pi system. The common naming for this is the number of atoms on each side of the sigma bond that's being broken and formed is how these are named. So in this case, we have 3 carbons on one side of the bonds being broken and formed, and on the other side we have 3, so this is a 3-3 sigmatropic rearrangement. So the naming is very straightforward as far as the systematic naming. If you can figure out which bonds being broken and formed, you can name these. Now notice I said atoms. This might contain an oxygen, it can contain nitrogen, so it's just the amount of atoms that are in each side of the bond being broken and formed. So for example, this one is a 1 and 5 sigmatropic rearrangement. The bond being broken is this carbon-hydrogen bond. The bond being formed is this carbon-hydrogen bond. So we have 1 atom on one side of the bonds being broken and formed, and then we have 5 on the other. So this is a 1,5 sigmatropic rearrangement. So again, that can be a hydrogen, it could be an oxygen, it could be a different amount of atoms. Notice that we're still retaining 2 sigma bonds, and we're breaking 1 sigma, forming 1 sigma, and retaining all of our pi bonds. There's no change in the pi bonds. So the most common sigmatropic rearrangement, there's 2 really common ones that we're going to focus on in a little bit more detail. And those are both what we call named reactions, meaning they're named after the scientists that first published them. But they can still be named in the systematic way, which is 3 + 3 sigmatropic rearrangement. Now notice I said the systematic naming could contain different atoms. These 2 name reactions we're going to discuss are both 3 + 3 sigmatropic rearrangements. However, one of them is going to contain an oxygen. But the formal naming system, 3-3 sigmatropic rearrangement, doesn't specify what the atoms are. So the actual named reactions do specify. So the COPE is a 3 + 3 sigmatropic rearrangement where all 6 atoms are carbons. So if we look here, what we see is under heat conditions, we can get this rearrangement. In general, the factor that's going to determine whether the product or the starting material is more stable, so where the equilibrium lies, is going to be your stability of your pi bonds. So we're starting with 2 pi bonds, we form 2 pi bonds, but If those pi bonds have different energies, then the ones that have the more stable pi bonds are going to be more there at equilibrium. So if we look at this one, we're starting with a monosubstituted and a monosubstituted double bond. But in our product, we have a monosubstituted and a disubstituted. So this double bond is more substituted, it's more stable. So for this case, the equilibrium would lie in the form of the product. So when we're determining which side the equilibrium will lie for this Koch rearrangement, it's going to lie to the side of the more stable pi bonds. Again, notice our mechanism. Here's our new bond forming. Here's the bond that broke. We do not have to draw it in this cyclic-like system, because remember, we do have free rotation around the sigma bond. For the reaction to occur, we have to have this structure. It has to be in this almost ring-like structure. But at any given time, which makes these reactions a little bit more slow, unless for some reason we have something that's keeping it in the structure, we can have this rotate to make the full linear compound. So keep that in mind. We do have free rotation. In our other examples, that wasn't necessarily the case, but here it is. So what we see in this case, 85% is going to be in this particular structure, just because the pi bonds are more stable. Now the second 3+3 or 3,3 sigmatropic rearrangement is the Claisen rearrangement, and that one is exactly the same except that it contains an oxygen. So we start with an ether linkage, and then we get the rearrangement to form aceto-O-butyl, so a carbon. And this could be an aldehyde or a ketone depending on what R groups are attached to this position. So again, the bond that's breaking is one of the carbon-oxygen bonds, and the bond that's forming is a carbon-carbon bond. And all we're getting overall is a rearrangement. We still have two pi bonds. Now in this case, the most important thing that's going to contribute is the stability of the pi bonds, and the carbon-oxygen pi bond is more stable than a carbon-carbon pi bond because it contains resonance structures. So because it contains resonance structures, remember a carbon-carbon pi bond does not have this as a resonance structure because there is no difference in polarity between those two carbons. So this is not stable. But a carbon-oxygen double bond, because the oxygen is more electronegative, has that resonance structure. This is our more contributing, but it does exist, and that helps stabilize the carbon-oxygen double bond. So because of that, thermodynamics of the carbon-oxygen double bond are more stable. So our carbon-oxygen double bond is going to be more stable for this rearrangement. If you start with an ester and you form the carbon-oxygen double bond, then that's going to be there in higher percent yield. So that's our Claisen rearrangement. But they're both very similar. The difference is this one has an oxygen. So if we look at this example, this one is a Claisen. Here we need our pi bonds that are reacting to be on the end. So again, this is our mechanism. The bond that's highlighted in black is the one that's breaking, and then we're forming a carbon-carbon bond between the pink end carbon and the blue one. So this is what that new product looks like, and this would be our more stable product than our starting material because we do form the carbon-oxygen double bond. Again, the arrows can be clockwise or counterclockwise in this case. And notice one thing I do want to point out. Especially with this one. Notice that the arrow is not pointing to the hydrogen. We're not forming a charged species. But it's that the electrons from this sigma bond is being transferred to form the sigma bond here. So notice that the arrow is not pointing to the hydrogen, and it's absolutely not coming from the hydrogen. It's always coming from the bonds, either the sigma bond or the pi bonds. It's not coming from an atom, it's not coming from lone pairs in all of these reactions. That is Same thing here. The arrow, the base of the arrow is on either a sigma bond or a pi bond. It's not on lone pairs. It's not on an atom. For all of these mechanisms. So you should be able to draw these mechanisms. Now this one is a little bit more complicated because of the way it's drawn. It's still a Claisen, but it's not drawn in the cyclic structure, which makes it a little bit harder to see. So one like this, the best thing to do would be to redraw it. Where our N double bond carbons, carbon 1 and 6, are next to each other. In that six-membered like ring structure. And I'm sorry, but apparently this thing isn't real calibrated this morning. So all I'm doing is drawing the groups that are connected to carbons 1 and 6, but they're just hanging out. So the ones in red are the ones that are actually reacting. So carbon 1 and 6 is going to be where our new sigma bond is. And we're forming a carbon-oxygen pi bond between 2 and our oxygen. And we break carbons 3 and 4. So when you draw that structure, what you get is C. So for these, if it's not drawn in that six-membered ring, the best thing to do is to redraw it, because that's the way it has to be to react in that mechanism. But most of the time, I'm nice and I draw it like this for you. But if it's not drawn like that, you do have to redraw it. Remember, we do have free rotation around those sigma bonds. Sigmatropic rearrangements are seen a lot in nature. For example, to form vitamin D, you actually have two pericyclic reactions that occur. You have this electrocyclic reaction here. And it's basically a reverse of one of our reactions. And then we have a sigmatropic rearrangement. And this is our bond breaking. And then this is our bond forming. So a 1, 2, 3, 4, 5, 6, 7. So that's a 1-7 sigmatropic rearrangement. Again, notice that the arrows are not coming from the hydrogen, it's coming from the bond. Finally forming vitamin D. So these are done in nature often. That's it for this chapter. I have a quiz for you for the rest of class. And again, the review is going to be tomorrow evening at 4:30 in this room. And I will remind you of that on Moodle.